Hello, I'm Dr. Michael Fossel. Most people think that while you might possibly be able to slow a disease progress in age-related neurodegenerative diseases like Alzheimer's, you can't possibly cure them. We think otherwise. And I'd like to go into this in some detail with you. I'm going to talk about the possibility of curing the dementias, which I think is an achievable goal. To do that, let me start by talking about what we mean by the dementias. Most of us are aware of, for example, Alzheimer's dementia and Parkinson's disease, as well as frontotemporal dementias and vascular dementias. Now, while each of these is a valid clinical concept or clinical syndrome, they often share overlapping features. For example, many of our Alzheimer's patients have motor components, as do Parkinson's patients. Many of the Parkinson's patients have what you might think of as cognitive deficits, for example, in executive function or memory. And the same is true of frontotemporal dementia, and many of these have overlapping components with vascular dementias as well. In fact, if you look a little more broadly at some of the other syndromes, and there are many more than just these, for example, Lewy body dementia and progressive supranuclear palsy and primary progressive aphasia, corticobasal syndrome, or posterior cortical atrophy, you find that again, these tend to have sort of mixed presentations often. Again, you do see patients with pure disease, but you also see many overlapping ones. So we often talk about atypical dementias, for which there are actually full global conferences, as well as the mixed dementias. And this has led a number of people over the past decade or two to feel that, in fact, all of these syndromes, these clinical syndromes, encompass something broader, which is, as I say, the age-related neurodegenerative diseases. And we think of them that way, age-related diseases of the central nervous system, dementias, for example. Well, part of the issue then is that many of us suspect there are deep fundamental pathologies that lie at the heart of all of these that are expressed in different ways clinically. And by clinically, I also mean the histology and the pathology of them, as well as the actual clinical syndrome. So there's something going on that's fundamentally the same, and yet they're expressed in slightly different ways clinically. And the question that comes up repeatedly is, why have we failed to make any progress, any inroads in treating these diseases clinically? And from my mind, I think that the reason is that we have an assumption of understanding. We tend to think that we understand to some degree these dementias. For example, we think of Alzheimer's as purely a problem with, for example, beta amyloid or tau tangles, or mitochondrial dysfunction, or inflammatory changes, or activation of glial cells, without going further. And the same thing is true of Parkinson's. We tend to see it as alpha-synuclein aggregates and substantia nigra, and failure of the neurons, and so forth. But we don't look more deeply, and we don't look for more fundamental shared pathologies among all of these syndromes. So as I said, part of the problem is what I call the assumption of understanding. And let me give you an example of this. This is a hill that many of you have heard of. Few of us have been to this hill. This is a hill in Scotland called Dunsinane Hill. Some of you will recall that in Shakespeare's Macbeth, the three witches told Macbeth that he would never actually be conquered until Birnam Wood came to Dunsinane Hill, which to his mind was clearly impossible. That is, he had an assumption of understanding, and the audience generally shared that with him until they were surprised, because Malcolm actually cut down much of Birnam Wood, used it to hide his soldiers as he marched on Dunsinane Hill, after which he conquered, in fact, killed Macbeth. So the issue often is that we think we understand what's going on, the audience in this case, or Macbeth in this case, but we do the same thing with regard to clinical disease. The same thing has occurred repeatedly in science. Here's an example with regard to flight. And Lord Kelvin, probably the world's preeminent physicist, made this statement some 8 years before Kitty Hawk, saying that heavier than air flying machines were impossible. Well, he was not a fool. He knew a great deal about weight, a great deal about air pressure. He was a little weak on aerodynamics. But the assumption of understanding he made was that things that are heavier than air cannot support themselves in air, which seemed, again, like a reasonable assumption, but it was false, proved by Wright brothers, Kitty Hawk in 1903, although it took the world probably about another 5 years before it became clear to everyone that, in fact, this had been accomplished. Well, the same thing is true of other parts of science. For example, our understanding of classical physics. The assumption in about 1900 was that we knew all about physics except for sort of dotting the I and crossing the T. And in fact, when you looked at atoms, they could be regarded as simply smaller components of what we're used to day to day. For example, billiard balls. So atoms were seen as very small billiard balls, and protons or electrons or neutrons were seen as even smaller billiard balls. Well, they're not simply billiard balls. They're not really balls at all. But it took until about 1924, before the first articles came out on quantum mechanics, followed by Schrodinger's equation here listed here, that gave us an understanding of what was actually going on with regard to atomic and subatomic particles, and in general, matter at that level. So we made the assumption of understanding based on our day-to-day workings of things around us, for example, this mouse. Well, atoms are not simply this mouse or a billiard ball. It was not until we had an understanding of that, until we achieved some understanding of the true physics, that we're able to have things like the computer I'm using now, or the Zoom call I'm on now, or in general cell phones, for example. So the assumption of understanding is often what stands in our way. And the same thing is true with regard to medicine. I began practicing medicine in the late 70s, early 80s, and in those days, the assumption we had with regard to pyloric ulcers and gastric ulcers was that they were caused by a combination of too much acid and simply stress. And that was an assumption of understanding that prevented us from looking more deeply. And it was not till this article came out in the British Medical Journal in 1983 by Robert Moran and Barry Marshall in Australia, in which they suggested that, in fact, pyloric ulcer, for example, was caused by the bacteria here on the right. This is Helicobacter pylori. It wasn't until that happened that we began to look back at our understanding, our assumption of understanding, and reevaluate it. And that's occurred repeatedly in medicine. We assume we understand it, and we don't look more deeply. Now, we do the same thing with regard to the dementias. As I say, we tend to assume that it's no more now than dotting the I and crossing the T, as we did with regard to classical physics more than 100 years ago. But it's our assumptions that really get in our way. We need to go a little further and try to understand at a more fundamental level what's going on in these diseases. This is a quote from a friend of mine, Dr. Leonard Hayflick. As some of you will recall, he was the one who first discovered cell aging back in about 1960, 61. He was also responsible for the WI38 cells, which gave access to, for example, oral polio vaccines. And what Dr. Hayflick and I were talking about a half a year ago was this, and his quote is correct. I think all of us tend to assume that age-related diseases, like the dementias, have their single greatest risk factor and their greatest predictive risk factor, aging itself. But we then entirely ignore the aging process, and we focus in on what are more trivial or downstream outcomes of the disease, for example, beta amyloid, tau tangles, alpha-synuclein aggregates, without asking ourselves, what does that have to do with the aging process itself? That is, we ignore aging, even while granting that it's the greatest risk factor, because it doesn't seem like a promising lead to us. And that's a mistake. Well, about a year and a half ago, the Alzheimer's Association asked me to go to Washington to summarize a talk. It was a conference we were having on animal models, in this case, Alzheimer's. And the problem that we have in the field generally is this statement: everything works in mice, but nothing works in humans. And the truth is, of course, not everything works in mice. But it begs the question of why is that true? Why is it that we cannot translate from mice to human clinical trials with any success? And I suggested several reasons. One reason that I noticed is that we share about 75% of the protein expressing genes with mice, and another 25% we do not. So there are fundamental processes, for example, mitochondrial function, that are shared between mice and humans, and cell aging, for example, in many respects. But there are other aspects of pathology and physiology that we do not share. For example, if I look at the processes involved in cortical decline with aging in mice, they do not have the same physiology for beta amyloid proteins that we have. So we tend to lay down beta amyloid aggregates, but mice don't have that same quite outcome. And the same is true of many other things. So there are certain things that mice do that humans don't, and certain things humans do that mice don't. The problem is we are not looking at fundamental processes. We tend to look at intermediate pathways which are not shared, rather than fundamental processes which are shared throughout many of these. So we need to look at the 75% of processes that are shared genetically, as opposed to 25% we don't. Now, the same is true with regard to human diseases. What we need to do is ask ourselves what's going on that's fundamentally shared between these diseases, rather than simply the disparate outcomes. So in Alzheimer's, you may have beta amyloid. In Parkinson's, you may have alpha-synuclein. The question is, what's going on at a fundamental level, rather than simply the intermediate pathways? And among those fundamental differences are cell aging. And they are all expressed in age-related neurodegenerative disease. So what I suggested that what we needed was a more fundamental understanding of what was going on in these disease processes. Specifically, we needed a unified systems model of what was going on in age-related diseases, and not only in humans, but in animals. And what we needed in such a model something that could explain, for example, heterogeneity within the dementias. So why is it that some patients get Alzheimer's at age 50 and others never get it even though they're more than 100 years old? Why is that different? Why do some patients with Alzheimer's have prominent beta amyloid and others don't, or get it later? Same with tau tangles, but also between dementias. Why is it, for example, that Lewy body dementia is slightly different in the pathology than Alzheimer's dementia? Why is Parkinson's different? Why is vascular dementia different? We tend to think we know this, but we don't look at a more fundamental level. And the same is true between species. What is it that's fundamentally shared between mice, humans, rhesus monkeys, dogs, cats, and so forth? Rather than simply looking at individual species, we need to have a model that can encompass all of these. We also need to be able to express and address the upstream mechanisms. So, for example, why is it that trauma to the head tends to increase your risk of Alzheimer's and Parkinson's? Why is it that certain central nervous system infections tend to increase your risk of many of the dementias? Why is it precisely that a history of hypertension and diabetes, that is hyperglycemia, tends to increase your risk of vascular dementias? How does that work? Likewise, downstream biomarkers. Why is it that some patients tend to have prominent beta amyloid and others lack that? Why is it that some patients have prominent findings that are not shared in different parts of the brain? Why do those occur? So we need a model that is unified and that explains all these, between the dementias, within the dementias, between species, upstream mechanisms, and downstream biomarkers. But it also needs to be a systems model. And by systems model, I mean, we can't be looking at simply the components like beta amyloid, but we need to look more deeply at the dynamic process in the biology that allows for this. To give you an idea of what I mean, let me use an analogy from engineering. You were looking on the left there at an Airbus 380 cockpit. Up above, you're seeing a Rolls-Royce Pearl 15 jet engine. In the lower right, you're looking at a Trent 900 turbofan and one of the turbofan blades. Well, a friend of mine who was responsible for overseeing much of the development of the Rolls-Royce jet engine and the Trent 800, in this case turbofan, said to me one day that what I was dealing with was a systems model of age-related diseases. And I asked what he meant by that, and he gave me an example. He said, when that single turbofan blade fails in the Trent 900 turbofan, he doesn't simply ask what's wrong with the shape and the metallurgy of the turbofan blade. He asks what's wrong with that turbofan blade in the Trent 900 turbofan, in the Rolls-Royce Pearl 15 jet engine, in the Airbus 380, at 35,000 feet, flying along 100 miles an hour between continents. That is, that turbofan is operating in a systems environment in which there are unusual temperatures. It's operating at high RPM. It's operating where there's a lot of vibration. So when that fan blade fails, the question is not what's wrong with the fan blade, but what's wrong with the fan blade in the system itself, that is the broader dynamic system. The same thing is true of aging. So here's another example. This is a river that many of you are aware of, probably few of you have seen. It's in the Congo, and that is the Ebola River. Reasonably enough, most of you will conclude that what I've got here is a list of signs and symptoms of Ebola virus, which is true. But those signs and symptoms are not Ebola virus. They're not the disease. They're simply signs and symptoms of the disease. The disease itself is a process. It's a complex interaction between the Ebola virus and a very complicated mammalian system, you in this case, that results in a cascade of pathology that's inordinately complex and often results in death, one of the symptoms and signs I didn't list here. So we cannot confuse signs and symptoms, that is downstream outcomes and biomarkers, with the disease process itself. Signs and symptoms are part of the disease, but they're not the process of the disease. We need to look more carefully. The same thing is true when we're looking at age-related diseases. These are common biomarkers at the macroscopic level of aging, things we're all aware of, for example, the decline in glomerular filtration rate in the kidneys, skin aging, poor healing, memory loss, all of these things, and many more. We see them in ourselves, we see them in those around us, we see them in our patients. But these macroscopic biomarkers are not aging. Biomarkers are not the process of aging. They are related to it, they are outcomes, they're correlates, they're associates, they're findings, but they are not the process of aging. Aging is not biomarkers. The same is true if I look at the microscopic level. So if I'm down at the histologic or genetic levels even, what you're finding is that there are literally hundreds of these findings that are biomarkers at the microscopic level. For example, decline in DNA repair, or declining ratio of ATP to reactive oxygen species, telomere shortening, acetylation changes. None of these are aging. They are part of aging, they're part of the overall process, they're components, they are biomarkers, they're signs and symptoms, but they are not aging. Aging itself is a process. And we need to critically distinguish the difference between components, such as these, and the process of aging itself. Many people would say what we're looking at then is a genetic process. And that's reasonable as a start, but the problem is these likewise are biomarkers of age-related diseases, such as in this case, the dementias. For example, beta amyloid plaque or tau tangles, mitochondrial issues, and so forth. These are all common findings in the disease process, but they are not the disease itself. And even if we specify at a deeper level, specify the genetics involved, these are still not the disease. Example, if I have a double ApoE4 allele, I've increased my risk of Alzheimer's disease. And if I have a double ApoE2 allele, I've decreased my risk of Alzheimer's disease compared to other people. However, we see patients with two ApoE4 alleles who never get Alzheimer's, and we see patients who do not have the ApoE4 allele who prominently have Alzheimer's disease. The same is true of many of these other genes, and I could go on again with many dozen, perhaps hundreds, of other genes that are genetically correlated with or linked to or associated with age-related dementias. These are not the disease. They're not causal. That is, having two ApoE4 alleles does not cause Alzheimer's, although it increases your risk and clearly plays a role, but it is not the cause of the disease. Because again, the correlation is by no means absolute. So what is really going on in the dementia process? Not simply the disease, but how do we get from the genetics of this to the disease itself? Well, in science, we often say that if you can't measure it, then it's not science. And in fact, that's certainly not sufficient. It's not enough simply to measure things. For example, in the 1500s, the Vatican astronomers had excellent measurements of planetary motions, but they had no understanding of celestial mechanics. They were adamant in their assumption that the Earth was the center of the universe, and the result was that while they had excellent measurements, they did not understand the solar system at all. The same is true in science in general. It's not a matter of measuring it, it's a matter of understanding your measurements. It is not simply enough to measure things in science. You need to understand what those measurements mean. And the same is particularly true with regard to medicine. Because if we don't understand the process, then we can't cure it. With regard to Alzheimer's disease and other age-related dementias, and in fact, age-related diseases in general, the only way that we can actually intervene effectively is not by simply measuring and having access to biomarkers and signs and symptoms. We need to actually understand the fundamental process, in this case, the aging process, and how it's expressed in the process of aging and the process or processes of age-related diseases. This is something that has worried me or concerned me for multiple decades, in fact, about 4 decades. And about 24 years ago, actually this April, I gave the first talk ever in the National Institutes of Health on the possibility for reversing the aging process at fundamental levels. And I started that talk with a remark that I want to make here and I will come back to in this talk, which is I said that anyone who left that talk and thinks you could reverse aging or could not reverse aging was naive. A sophisticated, rational response to that talk would be to say, maybe we can, maybe we can't, I don't know. Where's the data? It's the data that trumps everything in this case. Well, the other point I made was the same one, which is what is aging? What is the aging process? Not simply vague hand-waving about it being entropy or just happening, but what exactly is going on at the process level in aging. I think all of us are aware that aging works at different speeds, in a sense, in different species. For example, human beings have a typical lifespan of about 75 years. Gorillas typically about 40 years, 4 decades. In fact, that's Coco, the only gorilla in the world who spoke sign language. I was her babysitter for a year at Stanford. And I have to admit, she actually had a bigger sign language vocabulary than I did, which is humiliating, but true. Typical domestic species, cats and dogs, for example, tend to live about 2 decades, depending on the particular breed involved. Typical mice, rats, and other rodents that we're used to in the laboratory tend to live about 2 years or so. Well, you cannot simply say that aging just happens without explaining why does aging just happen in different species at different rates. Likewise, you can't simply wave your hands and say aging is simply entropy without explaining why entropy occurs at different rates in different species. And most of us, if pressed at this point, would say, well, aging obviously is genetic. Different species have different genes, and that's the outcome, although it doesn't express the combination between entropy and what's really going on with aging. But we would say it would be genes. And that's true as far as it goes. Although note that even when we share common genes within a species, we age at different rates. Example, these are a group of 30 progeric children that I brought together and took for a tour of the White House. Bill Sample there in the background with his hands up, and I got together every year with all of the progeric children in the world and took them various places. In this case, we took them for a tour of the White House, and I went places in the White House you are not supposed to go, and I took pictures of things you are not supposed to currently, at least, take pictures of. And we were having a delightful time with these children until Sammy in the front row with the red baseball cap and his friend Ori beside him in the Hawaiian shirt managed to sit down on a pressure sensor on the third step up just inside the north portico door there that leads up to the private quarters of the president. At which point the Secret Service very politely but quite firmly escorted us out the door. And here we are gathered. These children tend to die of age-related disease with an average age of 12.7 years. They're bald, which is why the only ones you're seeing with hair here are wearing wigs. They have, that's why they're tending to wear baseball caps and scarves over their heads. They have thin skin that doesn't heal well, prominent veins. They have osteoporosis, they have osteoarthritis. They overwhelmingly die of age-related vascular disease, for example, heart attacks and strokes. There's a 7-year-old in the back row who had a heart attack later this same summer that this picture was taken while throwing a baseball with his father in the backyard. Why is it that these children die overwhelmingly of age-related diseases, although they generally share the same genes you and I do? Well, we know the gene involved. It's a lamin A gene, and among other things, it's involved in telomere binding to the internal nuclear membrane. But knowing the gene does not tell us what's really going on with the aging process, nor does it tell us what's going on with the aging process in progeric children specifically. We need to go further than simply waving our hands and talking about finding a gene. We need to understand how that gene works with regard to aging. Many people think that aging is unavoidable, which is only true if you are naive and looking only at organisms you're used to. But if you look more carefully in biology, you realize that aging is by no means unavoidable. Example, every one of you has many, many cells in the body, literally trillions of cells, that derive from a single fertilized ovum that you inherited most of from your mother. And she inherited from her mother, and it was then a couple of decades old, and she inherited from your grandmother, and it was then a couple of decades old, and so forth. You can trace that line of germ cells back, unbroken, through 4.5 billion years of life on this planet. And during that entire 4.5 billion years, that germ cell line changed dramatically, but it did not show any evidence of aging whatsoever. And yet, there's a rapid inflection point in you and I a couple of decades back when many of our cells begin to show age-related changes. Why? Aging is not unavoidable. It seems to be fairly common in most of our cells, but it's not present in the germ cell line. The same is true of mitochondria. Many people would blame mitochondria for aging, and yet every mitochondria in your body at this moment was inherited from your mother, who got it from her mother, who got it from her mother, etc. And pari passu, the same thing going on in germ cells happens in your mitochondria. In this case, you can trace your mitochondria back 1.7 plus billion years. And during that time, the mitochondrial line showed no evidence whatsoever of aging. It maintains itself flawlessly in the face of entropy until a couple of decades ago when you inherited your mitochondria. And were I to test mitochondrial function in your body right now, and we'll come back to that, you'd find mitochondrial changes. Why did they not occur for 1.7 billion years, almost 2 billion years, and yet they occur in a matter of decades in many cells in your body? This is something that has intrigued me, as I say, for more than 40 years. I put out the first book ever on this aspect of reversing human aging now about 25 years ago, published the first part of articles ever in the medical literature on the prospects for reversing human aging at the genetic and cellular levels in the Journal of American Medical Association, followed by the first and still currently only textbook in this area with Oxford University Press. And it's a comprehensive book with some 4,700 references, and I wish you luck with it. It drives my graduate students up the wall. And finally, a book that came out a few years back for the general public that the Wall Street Journal called one of the best science books of the year. But this culminated, they all addressed this sort of question. It addresses this question of what is aging. That is, we know entropy plays a role, but what is entropy balanced against? And to answer that, to give a more complex answer of the process involved in aging, let me use another analogy, and that is the analogy of gardens, weeds, and weeding. These are actual pictures of my gardens. I have some very nice gardens, thank you. But they are nice not because they were planted well, but because they have continual maintenance. That is, it is not a matter of how many weed seeds blow in and how many weeds grow in my garden. It's a matter of maintenance. That is, how well do I weed the garden, as well as other things. So if weeds are entropy, maintenance is the weeding in this case. And the same is true of biological systems. If I'm looking at biological systems, what you find is that in the germ cell line, the balance between entropy and maintenance is flawlessly maintained and was maintained for, as I say, more than 4.5 billion years. And the same is true, as we'll see ultimately with regard to mitochondrial function. The same is not true of many of the somatic cells in your body right now. In this case, looking at an 80-year-old hand, and if you look carefully, you'll see that the melanocytes, the keratinocytes, the fibroblasts, all of the cells involved in that hand on the superficial level, to say nothing of the osteocytes and chondrocytes, have age-related changes. And the problem is not that they have entropy, because the germ cell line does as well. The problem is they lack sufficient maintenance, and the outcome is cellular dysfunction and age-related disease and age-related changes. Well, to give you a clear idea what's going on, take a look at the cells themselves and gene expression. In young cells tend to have long telomeres, and they have a specific pattern of gene expression that is characteristic of any given histology, any different cell population in your body. But it's also characteristic of age. There was a time a little bit more than a century ago when people thought that different cells in your body had different genes. And in fact, that's largely not true. Most of the cells in my body share the same genes, but they have markedly different patterns of gene expression. The same is true if we look at young cells versus old cells. If I look at the cell gene expression in the cells in my body when I was 10 years old, it is markedly different than the cells in my body as I turn 70 later this year. The genes themselves are largely the same. The pattern of gene expression is not. Now, the cells have shorter telomeres, and that plays a modulatory role in the pattern of gene expression. But the critical outcome here is the changed pattern of gene expression. It is not simply a matter of gene change, it's a matter of epigenetic change. To give you an idea of what I mean by that, I'm going to use another analogy, in this case, the analogy of a symphony orchestra. I can take a symphony orchestra and it can play very, very different tunes on different evenings, different scores. So for example, the exact same symphony orchestra might play Brahms one night and Haydn the next, or Glinka the third, or even Grateful Dead, or John Cage. The difference is not the instruments. The difference in the same sense between a young cell and an old cell is not that the violinist has gone deaf or the oboe is dented or the piano is out of tune. The difference between old cells and young cells is that they're playing a different score. And that score is set by the conductor, in this case, the telomere. But it is a difference in score that creates that difference in what they're playing each night. So the difference between a young cell and an old cell is not the genes, it is the pattern of gene expression, because the conductor, in this case the telomere, chooses the score, it sets the tempo of gene expression. Now, to give you a clearer idea at the very fundamental level what's going on, I look at any molecular pool in your body, and I don't just mean between cells or within cells, but both. Example, if I'm looking at young cells and I'm looking at the collagen and the elastin in my skin between the cells, they are being turned over. And the rate at which the molecular pools, collagen and elastin, are being turned over is very fast in young cells with long telomeres. Now, the same is true if I'm looking at beta amyloid, or I'm looking at, for example, mitochondrial enzymes, for example, aerobic enzymes, cytochrome oxidase within my cells. In any molecular pool, you find they're continually being turned over dynamically. So again, if I'm looking at my collagen, this is not the same collagen set of molecules that I had at age 10. The molecules I had now as I approach age 70 are very different molecules. They're continually being turned over, and the rate of turnover actually has slowed down considerably. Now, in young cells, when there's damage to one of those collagen molecules, for example, as I grin and move my face back and forth, if there's damage to those molecules, it tends to get washed out because the molecules are continually being recycled, if you will. So if damage is signified here by that red star, in a young cell, that damage is continually being washed out as the molecules are replaced, recycled, or turned over. But as telomeres shorten, they have an effect on the pattern of gene expression. And the major part of that effect is to slow the rate of molecular turnover in any molecular pool we look at. So as aging occurs, you begin to find that while the rate of turnover goes down, or recycling, if you will, the damage begins to accumulate, whether that's damage is oxidative damage or whether it's simple cross-linking of molecules for a number of reasons. And in very old cells, the rate of turnover is slow, and so the rate of accumulation, or the total accumulation at equilibrium, is much higher. We can even look at that in a mathematical way. This is a formula taken from my textbook. And what it really says in simplistic terms is, in young cells where there's a rapid rate of turnover, then at equilibrium, the accumulated damage is very small. Whereas if I slow the rate of turnover in an older cell, for example, you find that at equilibrium, again, the accumulated damage is very high. And the outcome of that are not only dysfunctional molecules, but dysfunctional cells culminating in age-related disease. Let's look at an example of that. In this case, we're going to look at Alzheimer's dementia. I think most of us are aware that one of the features of Alzheimer's dementia, in fact, one of the early features, is beta amyloid, first microaggregate and then actual plaque formation. And if we look carefully at the physiology of beta amyloid, what you find that it is also being continually recycled. That is, the microglia in this case are continually producing beta amyloid, excreting into the area around the neurite, then rebinding it, taking it up again into the microglia, and then degrading it. And this is a closed loop. It's continually being turned over. And the result of that is that even when there's damage to one of those beta amyloid molecules, it tends to get broken up. It's internalized, degraded, and replaced. But as we get older, what you find is that the rate of turnover in senescing microglia, long before they become replicatively senescent, but as they're beginning to senesce, the rate of turnover slows down. We've measured this, and you can see the production, binding, uptake, and degradation rates all fall. And the result of that, as I've said, is that you begin to get damage that's not being turned over rapidly enough. So at any given equilibrium, any given age, if you will, you tend to get slight increase in the formation of beta amyloid microaggregates. You might ask yourself, what's that could do with the genetic risks involved? Well, as I mentioned, if you have two ApoE4 alleles, you have higher risk. If you have two ApoE2 alleles, you have lower risk. Well, those with two ApoE2 alleles, for example, tend to make beta amyloid molecules that are not, relatively speaking, sticky. So they don't tend to cross-link and bind and form beta amyloid microaggregates as much as they might if you had a different gene. The result of that is that in patients with two ApoE2 alleles, you have very little in the way of entropic damage. And so even when you slow the rate of turnover of these molecules, beta amyloid microaggregates tend not to form. So these patients tend not to get beta amyloid microaggregates or beta amyloid plaque, even though they may be 100 years old. Whereas if you have two ApoE2 alleles, you tend to make molecules, beta amyloid molecules in this case, that tend to cross-link much more readily. The outcome of that is that even at younger ages, for example, age 50, you may also see not only that they have the gene, but that they're beginning to actually produce beta amyloid microaggregates, because the slight slowing in the rate of turnover is sufficient to allow increase of damage accumulation in the area around the neurites. Well, the same is even more true as this slows further and you get older. So for example, an 80-year-old will have a much slower rate of turnover of the beta amyloid molecules, and it's partly dependent on the genes and the risk factor, but the most important feature is how fast this is being recycled. And the result then is that not only do you have these microaggregates form, but as you get more and more of them, you begin to get frank beta amyloid plaque. And the same thing is true whether we're looking at beta amyloid or tau tangles, mitochondrial function, which we'll come back to in detail, inflammatory changes, or any of the other biomarkers that we see prominently in almost any age-related dementia we look at. And the outcome of that, of course, is you begin to get synaptic loss, dysfunctional neurons, dead neurons, loss of neurons, and frank clinical findings, that is, dementias of various sorts. But all of these ultimately can be traced not only back to the individual molecular pool, but to the slowing in the rate of recycling or turnover of these molecular pools. But the same is true with regard to mitochondrial function. So while we've looked at some of the things outside the cells, that it is the extracellular volume, within the cells, we can look at any number of molecular pools, or we can look, for example, at mitochondrial function. Only about 1% of the mitochondrial enzymes responsible for aerobic metabolism are actually coded for within the mitochondria. And it's an interesting question about why. It has to do with rapid feedback necessary in certain cases, for example, transient loss of oxygen compared to, for example, thyroid function, which tends to be a slower onset. But 99% of the mitochondrial enzymes for enzymatic function in the mitochondria derive from the nucleus, and they are slowed down in the rate of recycling. So although you're continually producing these molecules and degrading them, the rate of turnover is slower. And so when there's oxidative damage, which occurs all the time in mitochondria, these are not being turned over as fast in older mitochondria as they are in younger mitochondria. Well, the outcome of that is that you're less efficient at making ATP. And because there's some sloppiness involved, you tend to get more and more in the way of free radical formation within the mitochondria. Nor is that the only problem. The lipid membranes that bar the free radicals from getting out into the cytoplasm are also being turned over. The lipid molecules in that the double membrane around the mitochondria are being slowed in their recycling rate. So as they begin to show oxidative damage, the mitochondrial membrane becomes leakier. So you're not only making more free radicals, but you're leaking them more frequently into the cytoplasm, where you have scavenger molecules, for example, catalase, superoxide dismutase, glutathione. And these molecules are also being turned over more slowly. So the outcome is that when the scavenger molecules get damaged, they're not being replaced as quickly, so you're less and less efficient at scavenging free radicals. So you're making more, you're leaking them into the cytoplasm more, and also into the nucleus, which we'll come back to in a minute. You're scavenging them at a slower rate. And when you cause damage to other molecules, they're being turned over at a slower rate. So you have more and more, in fact, exponentially more, in the way of damaged molecules, and therefore dysfunctional molecules and dysfunctional cell function. Well, within the nucleus, you actually have molecules that you not only turn over, but you actually repair. And in fact, in the past 35 minutes since I began talking to you, every cell in your body has had DNA damage in the chromosomes. And you have almost certainly flawlessly repaired it almost instantly in your cells. But as you get older, the rate of repair slows down. So rather than occurring in a matter of seconds, it may take a matter of minutes. And this is true of all four of the families involved in DNA repair. So you have detection enzymes, excision enzymes, replacement enzymes, and ligation enzymes responsible for repairing DNA damage as I'm talking to you. Well, all four of these families are slowed down in their rate of molecular turnover. So again, there's an exponential increase in these, but each one is an independent factor. And the outcome of that is you get an exponential increase with aging in DNA damage, which results in an exponential increase in malignancy or frank clinical cancer. And it is not a matter of time, it's a matter of DNA damage. So for example, mice have an exponential increase in malignancy over 2 years. You and I tend to have it over 100 years. It is not the time per se that's the problem. It's the fact that DNA damage is not being repaired as readily as it was in younger cells. Another way to put this might be that your risk of cancer is not, strictly speaking, a matter of lifetime exposure to carcinogens. It's a matter of your ability to repair the damage as a result of exposure to those carcinogens. So the rate of cancer with aging, as opposed to genetic damage that you inherited, but rate of damage and aging malignancy is related to cell aging. Now, I want to clarify a couple of misconceptions. One is I want to make it clear that telomeres do not cause aging. Telomeres no more cause aging than genes cause evolution. Genes play a key role in evolution, but they're not the cause of evolution. They're a key player. Telomeres do not cause aging. They're simply a key player in it. In fact, the entire concept of causation is simplistic in this regard. The matter of how evolution works is inordinately complicated and interesting. The matter of how the aging process works is likewise complicated. It is not simply a matter of billiard balls, A causes B, causes C, causes D. It is actually not linear at all. It's a complicated dynamic process. And again, telomeres play a role, but they're not the cause. Anything more than anything else is the cause of aging, or aging diseases for that matter. Likewise, I want to make it clear that telomere length doesn't matter. The change in telomere length matters. Absolute telomere length is irrelevant. Relative telomere length is crucial. For example, you can predict lifespan of almost any given mammal you want to on the basis of the rate of telomere loss, not telomere length, but the rate of telomere loss. Because again, that's what affects the rate of gene expression. To give you a clear, specific biological example, there are mice varieties that have telomeres that at birth are 10 times my telomere length, and yet I have a lifespan that's approximately 40 times that of the average mouse. It is not telomere length that matters. Telomere length is irrelevant. It's a matter of the loss of telomere length, or the relative telomere length, or more specifically, the effect that telomere changes have on gene expression. Now, let's look at a more complicated way of viewing aging, both upstream and downstream. What you're looking at here is a figure actually taken from a recent article that I published that I'll come back to. And what it really says is there are a number of upstream factors that play a role in cell aging, and there are a number of downstream outcomes. Upstream factors, for example, include things like genetic predispositions, trauma. For example, if you have head trauma, you increase your risk of Alzheimer's or Parkinson's. Toxins, for example, there are herbicides that will increase, for example, paraquat, increase your risk of Parkinson's disease. We know that hyperglycemia or hypertension can increase your risk of vascular dementia. Radiation exposure, infections, for example, the CNS can increase your risk of onset and your rapidity of onset for a number of age-related dementias. And the same is true of any number of age-related systems elsewhere. For example, trauma to the knee will increase your risk of osteoarthritis because of the impact it has literally on chondrocytes in the knee and so forth. But all of these are not the cause, they are contributive causes, and they play a role at various levels in the increase in cell turnover, shortening telomeres, altering patterns of gene expression, cellular dysfunction, and ultimately the downstream outcomes, including clinical outcomes. But to look at some of the downstream biomarkers, we see, for example, beta amyloid plaque, tau tangles, mitochondrial dysfunction, alterations in DNA repair. And we could list literally hundreds of these as downstream biomarkers, outcomes or signs and symptoms, or differences in histology or pathology. But they are downstream outcomes of the central process, which is cellular aging. Now, one of the questions you might ask is, how do we have an impact on this clinically? Because in many ways, what I've just said to you doesn't matter to me. My major question is not really what causes aging. The question is, where's the single most effective point of intervention clinically and financially if we wish to show that we can cure, prevent, or otherwise improve age-related diseases? Well, one of the places we look are upstream targets. And we've looked at this for as long as we've had medicine in this world. As one example, we know, for example, that if I decrease your blood pressure and lower your blood sugar, I can decrease but not prevent the onset of age-related vascular dementias. The same is true of trauma. If I prevent head trauma, I lower your risk of Alzheimer's and Parkinson's, but I don't prevent it. We see patients who have no head trauma who have Alzheimer's. We have patients with Alzheimer's and no history of head trauma. The same is true of exposure to toxins or chemotherapy or certain genes, as I've already alluded to. So all of these are upstream targets that have an effect on the overall disease process involved that has a narrow point in cell aging, but none of them are the cause, and they are inefficient targets. No matter what we do upstream, we find we cannot prevent. We can ameliorate or slow or decrease the risk of, but we don't actually prevent age-related diseases, let alone the age-related dementias. The same thing is true of downstream biomarkers. Attacking downstream biomarkers as a primary clinical target is inefficient. Example, there have been more than 1,100 registered trials for Alzheimer's disease looking at beta amyloid, tau tangles, mitochondrial dysfunction, and none of them has, by global consensus, shown any impact on the course of these diseases. The same is true of anything else I look at. For example, working on just reactive oxygen species. None of these have been shown to be efficient in preventing or let alone reversing age-related diseases such as the dementias. In fact, the single most effective target, the optimal target, is the cellular aging process itself. And I say that not for theoretical reasons, but because it's actually effective. We have known now for approximately 22 years that we can reverse cellular aging in human cells in the laboratory. We've known for 20 years this year that we can reverse aging in human tissues in the laboratory. And we have now known that we can do the same thing with organisms, for example, mice, for now 9 years, and an even better model now 8 years ago. So there's good solid data and there's good proof of concept. In fact, we know that if we're looking at age-related cognitive decline in animals, that using telomerase therapy, we can not only reset senescence in cells, but restore neural function and reverse cognitive decline in animals, which is why we intend to take this to human trials and show we can do the same thing with human disease. Well, this is what prompted me to write this article based on that talk I gave in Washington for the Alzheimer's Association, after which I was invited by the editors of Alzheimer's and Dementia to write this article. And this article has several features that are noteworthy. One is, it's the only article ever to offer a unified systems explanation, a model, if you will, for how age-related neurodegeneration works, not only in all human diseases, but in animals as well. And it's entirely consistent with all known clinical and research data in this area. And it's actually been predictively valid in predicting ahead of time the outcome of, for example, the Eli Lilly solanezumab trials or the Biogen Eisai anakinumab trials, as well as others. But more importantly, it offers a feasible, innovative, and in fact practical and probably effective point of intervention for the age-related dementias, which is why we're going to take this to clinical trials, as I say. The publication of this article resulted in global requests for reprints, more than 600 global requests, and more than 24 requests for me to give keynotes, which I've largely declined, and considerable interest from investors. More importantly, though, it offers a model for how we're going to take this to human trials and show we can do it. So this is what we'll be using. We'll be using a single dose gene therapy. It'll be an adeno-associated virus initially, an AAV9, although there are other approaches that may be more effective in the long run. We'll be using a standard human telomerase gene and a promoter. And our primary target strategically initially will be the dementias and hence glial cells and neurons. I have already talked to the FDA and CBER in Washington. We're ready to proceed with our application and take this to FDA human trials. Well, as I said at the NIH 24 years ago, and I say again to you now, the question isn't, can we do this or not? The question is, what does the data suggest? Well, the logic for this model is overwhelming. And again, it's the only model that's entirely consistent with all known data and offers an effective point of intervention. But logic is excellent, but as I've always said to my graduate students and my residents, data is best. Data wins every time. So the question is, what happens when we take this to human trials? Can we show we can do it? I think we can. And for the first time in history, I suggest that we have an effective point of intervention for age-related dementias, and in fact, for age-related diseases generally. Thank you very much for joining me, and I hope that you've enjoyed the discussion.